Okay, now the statistical mechanical definition of entropy I gave you guys the last time, which looked something like this: S equals K natural log W, is extremely useful for providing you a way to develop an intuitive feel for what entropy means. It's this connection between the system degeneracy, remember, and disorder, right? So that entropy, then we can of course think of as connected to or proportional to disorder. Okay, but there's a problem with stopping here and thinking about entropy. Um, Measuring the system degeneracy intrinsically is something that's just in principle, except for certain limited systems or in theory, is just not something you're going to be able to do quite readily, right? So we still need another state function in order to measure something that will allow us connect this idea of entropy to the larger question of spontaneity, which is where I left you guys the last time. Remember that changes in heat flow alone do not accurately predict whether a process is going to be spontaneous or not. Remember my ice cube example. We'll come back to that in a moment. Okay, so we need another state function of some kind. So at this point, what we need to do is turn back to the classical definition of entropy. This is the definition that was developed as a result of a lot of careful and hard work by a number of people beginning the late 19th century and on into the 20th century, thinking about heat engines, right? And that definition looks something like this. The differential change in entropy is exactly equal to the amount of heat gained or lost by a reversible process divided by the temperature at which that process occurs. So again, we're working at constant temperature and working at constant pressure. And if you remember from your physical chemistry, a reversible process is one of these theoretical ideas where some transition between two states is carried out through some infinitesimal differential number of steps, right? It's the maximally efficient way a process can be carried out, and it doesn't exist in the real world, right? But it's possible to prove that the differential change in entropy is exactly equal to the differential change in heat of that reversible process. Now, like I said, because what we're interested in is the real world processes, and specifically, we're interested in real world and spontaneous processes, right? The importance of sort of a reversible process as more than just a construct for us is less obvious. But it's possible to show that in the real world and for spontaneous events, the amount of heat gained or lost by a real world and spontaneous event is always going to be less than the amount of heat gained or lost by the same process done reversibly, right? And because that's the case, the following has to be true, which is that the change in entropy for that reversible process, or the change in entropy for that real world and we'll just say that spontaneous process has to be greater than the heat gained or lost by that real world spontaneous process divided by the temperature at which it happens. Okay, now, if that's the case, we can think about that transition from, say, state one to state two for a spontaneous process we really care about. If that's true, that this relationship holds, that means the following also has to be true, that the entropy in state two minus the entropy in state one has to be greater than that heat gained or lost divided by the temperature. But we remember from the first law, right, that the change in energy is just equal to the heat and the work done from the first law. So we can combine these two, right? And when we do, what we can see is that that change in entropy has to be greater than the change in internal energy in a spontaneous process minus the work done, again, we're at constant pressure, divided by the temperature at which the process is taking place. Now, notice I'm using the sub P, I just mentioned it. We're thinking about this as under conditions of constant pressure because that's the condition where life is going to be most relevantly configured under constant pressure as we thought about it last time. Okay, so we can constrain this a little bit more. Remember, we're going to only allow pressure volume work. And if you recall from last time, if we only allow pressure volume work, then our definition of work looks something like this, minus P delta V. Okay. So now we can combine these two together, and that relationship now looks something like this. S2 minus S1 has to be greater than combining this definition for work, the definition for work, along with that modification, bringing the first law into the equation. And the relationship now looks something like this. E2 plus PV2 minus E1 plus PV1 divided by T. Well, if you remember from last time, when we talked about constant pressure, that relationship, those expressions here and here, we defined as something. Remember, that's the enthalpy, right? So that would be the enthalpy for state two, that'd be the enthalpy for state one. That means we can write this a slightly different way, where S2 minus S1 has to be greater than H2 minus H1 divided by the temperature. And if that's the case, we can multiply this through so that S2 minus S1 times the temperature must be greater than H2 minus H1. That's cool, because we can now rearrange that to say, well, that has to mean that H2 minus H1 minus T times S2 minus S1 has to be less than 0. Or written out another way, for any real world spontaneous process, the following must be true: that the change in enthalpy minus the temperature at which the change of state takes place times the change in entropy has to be less than 0. Now, enthalpy is a state function, right? Entropy is a state function. Any combination of state functions is also a state function. And we, or more correctly, the 19th century physicist by the name of Gibbs, who first put these ideas together and derived this relationship, this new state function gets a name, and it's known, of course, as the Gibbs free energy. And it gets the symbol G. Right? And the Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. Or more usefully, in thinking about things happening, spontaneous processes taking place in biology, which is really what we care about, delta G equals delta H minus T delta S, right? Now, that's a really important relationship. If you don't know it, you don't remember it, you should remember it. You're going to need it. Okay. So let's think about some of the properties of the Gibbs free energy for a minute. Okay. So if the free energy change for some process, let's say A goes to B, the way I've written it here. If the delta G for that relationship is less than 0, what does that mean? It means this process is spontaneous. If, however, the free energy change is equal to 0, what does that mean? That means the process, of course, is at equilibrium. And finally, if delta G is if delta G is greater than 0 for the process as I've written it, what does that mean? It means that the reverse process specifically B goes to A in this case, is spontaneous. Okay, so let's go back now to my glucose and phosphate example, right? So with that set of ideas, if we go back and we think about that critical initial metabolic reaction, glucose plus inorganic phosphate goes to glucose 6,6-phosphate. Remember I said it didn't work if you just mix them into the test tube. Well, if one goes and actually measures the free energy change for that reaction as written, turns out delta G is plus 14 kilojoules per mole. So now we know why the process doesn't happen. It's energetically so unfavorable that it's just not going to happen on any timescale relevant for any organism on this planet, all right? It's never going to happen that way. Now you can say, well, wait a minute, wait. You're saying it's never going to happen. It's impossible. But you're also saying that, come on, Dr. I, that it's essential, that life can't exist without it, right? That's a contradiction, right? Well, not necessarily saying it's impossible fundamentally, it's just not going to happen written like that, right? It's simply non-spontaneous under that set of conditions, driving energetically unfavorable reactions with energetically favorable ones, coupling energetically unfavorable reactions to favorable ones is one of the central themes of basic biochemistry. And in this case, that coupling looks something like this. We take glucose plus ATP, a hydrolysis of ATP to ADP and inorganic phosphate has a free energy change that's extremely favorable. In fact, it's about minus 17 kilojoules per mole. So that this overall process of taking glucose plus ATP to form glucose 6-phosphate and ADP has an overall free energy change of minus 17 kilojoules per mole, which is quite favorable, right? Okay. So some final thoughts about free energy. So knowing delta G, right? Knowing the value of delta G for a reaction tells you whether a process is, as written, is spontaneous or not, right? However, it tells you absolutely nothing about how fast that reaction is going to go, okay? So the free energy difference between the products and reactants of reaction tell you whether or not that reaction can go the way it's been written down, but you know nothing about how quickly the process will take place. Okay. Second thought, it's kind of a question. Can the entropy of a closed or open system ever go down? In other words, can delta S ever be less than 0? Think about that for a second. What trips a lot of people up in thinking about this question is considerations of the second law of thermodynamics, which say that for any spontaneous process, any real process in our universe, the entropy of the universe has to go up. But that doesn't mean the entropy of some system within the universe, some open system or closed system within the universe, the entropy can't locally go down. It absolutely can go down. It does all the time, provided that change in entropy is paid for. Here's a good example. Think about my example of ice formation at 0 degrees. Does the entropy of the water that's freezing go down? It absolutely does. And the reason that's possible is because the enthalpy change, the release of heat when you form those hydrogen bonds in that crystal, is much more favorable at that temperature than the disorder of the water. So this yin and yang, this trade-off between entropy and enthalpy, is a theme we're going to be coming back to over and over again as we go on and we talk about protein dynamics and folding, and as we talk about binding and all kinds of other processes. So the answer to my question is, can it ever go down? The answer is absolutely yes, it can, if it's paid for. Okay. So third thought about free energy, right? As I mentioned before, the sign of the delta G for reaction tells you whether the forward or reverse process is spontaneous, right? And finally, the magnitude of the free energy change tells you a couple of things, right? The magnitude of the delta G tells you, one, tells you how much energy you have to work with. Right? So the larger that magnitude, the greater the delta G value is away from 0, tells you how much energy in principle you could tap in moving that process towards equilibrium. The other thing it tells you, right, sort of a corollary of the flip side of that exact point, is it tells you how far a process is from equilibrium. So that idea of equilibrium, right, is super important, right? And the connection between equilibria and free energy is a really, really critical topic to sort of get your brain around, right? So that's what we're going to talk about next.